All right, welcome back. So this time we're going to go into L1 and L2 regularization. But before we get started, hit the like button, subscribe, and share this with anyone you know taking the AWS Machine Learning exam. So L1 and L2 regularization prevent overfitting by penalizing large model weights. Overfitting occurs when models learn training data patterns too specifically, including noise, resulting in poor performance and unseen data. These techniques apply across linear regression, logistic regression, support vector machines, and neural networks trained in AWS SageMaker. Both methods discourage complex models by adding penalties to the loss function during training, but they differ fundamentally in how they constrain model weights. First, we'll go into L1. So L1 regularization, or Lasso. Let's see if we can find this. All right. All right. Okay. So this adds a penalty to the absolute value of a weight magnitude. So the loss equals 0, right? So this penalty encourages sparsity, where many weights become exactly 0, effectively removing features from the model. L1 performs automatic feature selection, making it valuable when you believe only a small subset of features matters. Consider a dataset with 100 plus features where only a handful drive predictions. L1 regularization zeroes out irrelevant feature weights, producing a sparse model with fewer active predictors. This simplification may initially increase compute time due to iterative weight shrinkage, but the resulting model trains and infers faster. Then you have L2. Let's see. So L2 adds a penalty equal to the square of weight magnitudes. Unlike L1, L2 doesn't zero out weights. It retains all the features while shrinking some weights towards 0. This produces dense models where every feature contributes, though some contribute minimally. L2 is computationally more efficient than L1 and works well with curated datasets where every feature adds value. When you expect all features to contain useful information, even if some are less important, L2 maintains those signals while preventing any single feature from dominating unless strongly supported by data. So, choosing between L1 and L2. L1 creates sparse models through feature elimination, making it ideal when you need interpretable or suspect many irrelevant features. L2 creates dense models that retain all features, suitable when every feature provides a signal. L1 has higher computational costs, but produces simpler downstream models. L2 is more memory and compute efficient, often preferred in large-scale applications unless feature selection is critical. Sparse models from L1 reduce inference costs, particularly valuable in edge devices or real-time systems where computational resources are constrained. So how does this work with AWS? Built-in algorithms like Linear Learner and XGBoost support both regularization types. You can tune L1 and L2 hyperparameters directly. SageMaker Autopilot automatically considers regularization when selecting and configuring models. Hyperparameter tuning jobs can explore ranges for L1 and L2 to find those optimal values. Regularization improves generalization, reduces training frequency, and decreases false positives. These are all factors that lower operational costs in production machine learning systems. So when you're using this, how do you go about hyperparameters? All right. So this is what we're talking about. Rather than manually testing regularization values, you can use SageMaker's hyperparameter tuning jobs. Define ranges for L1 and L2 parameters. For example, you can have L1 from 0.001 to 1.0 and L2 from 0.0001 to 0.1. Set your objective metric to validation accuracy or validation loss. The tuning job explores combinations using Bayesian optimization, identifying the regularization configuration that maximizes generalization. This automated approach saves time and often discovers non-obvious parameter combinations that manual tuning would miss. So, what are the costs here? Regularization delivers multiple cost benefits. Better generalization reduces training and retraining frequency, saving compute costs over the model lifecycle. Sparse models from L1 decrease inference latency and costs, particularly valuable at scale. Fewer false positives reduce downstream operational costs in production systems. And so these upfront investments in proper regularization can pay dividends throughout the model's operational life. So for the exam, when you see any questions that ask about preventing overfitting in linear models, performing feature selection, or choosing between sparse and dense model representations, understanding L1 and L2 regularization will guide you to the correct answer. That's all for this lesson. Thank you for joining. Hit the like button, subscribe, and share this with anyone you know before we go. And if you're going to take the AWS Machine Learning Associate exam. Thank you, and have a good day.